Welcome you all for this online class. Today for Control Systems Engineering subject, we are going to discuss about what do you mean by mathematical model of a control system, then what do you mean by mechanical systems, and the mathematical model of mechanical translational system. First of all, we are going to see about what do you mean by mathematical model. So as I explained already, the control system is an collection of a number of components. Each component is having an input as well as output. The input as well as outputs are related by means of a mathematical equation that is called a differential equation, which is the mathematical model of the control system. So the control system can be either a time invariant system or it can be a time variant system. So what do you mean by time invariant system? So in time invariant control system, the coefficient of the differential equation governing the system will be a constant. For example, consider this differential equation. Here, the coefficients are 1, 10, 5 as well as 2. So all these coefficients are constant. So the corresponding system will be an time invariant system. Here y of t represents the output of the system and x of t represents the input of the system. Input and outputs are related by means of a differential equation. The next one is time variant system. So in a control system, if the coefficient of the differential equation governing the system is a function of time, then we can say the corresponding system as a time variant system. So consider this differential equation. Here the coefficients are 1, t, 1 as well as 10. Here one of the coefficient varies with respect to time. So such type of system is called the time variant system. Now we will see about what do you mean by transfer function of the system. To analyze the control system mathematically, we have to find the transfer function of the system. So the formula for the transfer function will be Laplace transform of output of the system divided by the Laplace transform of the input of the system with zero initial condition. So to find the transfer function of a particular system, we should know about how to find the Laplace transform. So in short, we can write it as L of output divided by L of input with zero initial condition. Next, the mechanical systems. So in the introduction class, I have told all the mechanical machines are the mechanical systems. There are two types of mechanical systems, mechanical translational system as well as mechanical rotational system. So in the mechanical translational system, the input will be a linear force that is represented by F, and the output will be a linear displacement which is represented by X. So in a mechanical rotational system, the input will be a twisting force that is nothing but torque, and the output will be an angular displacement that is represented by theta. Okay, so first of all, we are going to see about the mechanical translational system. So in the mechanical translational system, the input will be a linear force, output will be a linear displacement. So all the mechanical machines in which that is the mechanical machines in which if you are having the input as a linear force as well as output as a linear displacement, then we can say it as a mechanical translational system. So now the mechanical translational system can be modeled by using three elements, that is mass, dashpot as well as spring. So first we are going to see about what do you mean by mass. So if you are considering a mechanical machine or a mechanical body, it is having a weight. So weight of the mechanical system is represented by mass, and the mass will be measured in kilogram. Then dashpot. So in the mechanical machine, if there is any friction existing in the rotating part of the system, then there will be a dashpot for that corresponding system. So the frictional coefficient will be measured in Newton second per meter. So now the spring, that is elastic deformation of the mechanical system, will be represented by K, and the spring coefficient will be measured in Newton per meter. Now the input will be a linear force that we know on the mechanical translational system, that is F. Instead of saying it as F, we can say it as an F of t also, because for all the control system, the input varies with respect to time. Similarly, the output for the mechanical translational system will be a linear displacement that is represented by X or X of t. Both input as well as output will vary with respect to time. But simply we are saying it as F as well as X. So now the different components of this mechanical translational systems are mass, dashpot as well as spring, isn't it? So first, the representation of mass. So if we are considering a mass, it will be represented by a small box like this. Inside this, you have to write the value of m. Now the dashpot will be represented by the symbol like this, which is similar to the piston which is moving inside a cylinder. So here there will be a friction existing between the piston as well as cylinder. That is nothing but the frictional coefficient. Now this is the representation of a spring, that is K. Next, now we are going to consider one mechanical translational system which is having a weight as well as dashpot as well as spring. That is mass, frictional effect as well as elasticity effect. For this mechanical translational system, we are applying a linear force F. When we are applying a linear force F, due to that there will be a linear displacement X. This applied force will be opposed by the opposing forces which is generated inside the body. So this mechanical system is having the effect of M, B and K. So it will produce an opposing forces of Fm, Fb as well as Fk. Now this is the representation of F, that is input force. F is an applied force, then Fk is an opposing force due to spring, and Fb will be the opposing force due to dashpot, and Fm will be the opposing force due to mass. Now to determine the force acting on a body, we have to use Newton's second law. Newton's second law states that the sum of the force acting on a body is equal to 0, or the sum of the applied force is equal to the sum of the opposing forces. We can use any one. So which is similar to the Kirchhoff's current law. At a particular junction, algebraic sum of the current will be equal to 0, or at a junction, sum of the incoming current is equal to the sum of the outgoing current. Now, when we are applying a Newton's second law here, only one applied force, that is represented by F, and 3 number of opposing forces, Fm, Fb as well as Fk. The sum of the opposing forces will be Fm plus Fb plus Fk. So now what we are going to do is we are going to see the force balance equations for idealized element. We are considering a mechanical body or the mechanical system which is having a single effect, that is only one effect, either a mass effect or frictional effect or elasticity effect. First we are going to consider the mass effect, that is opposing force due to mass. So to derive the opposing force due to mass, what we have to do is we have to consider the mechanical system which is having only the effect of mass. So it is represented by an M like this. One end of this mass is connected to the fixed reference surface. This is nothing but a wall. That's a representation of wall. Then at the free end, we are applying an input applied force, that is F of t. Due to this applied force, the mass will move at a distance of x or x of t. Now this force will be opposed by the opposing force due to mass, that is represented by Fm. This Fm will be directly proportional to the acceleration of the body. Now you know, if a body is displaced at a distance of x, from this we can find the velocity of the body, that is dx by dt. And the rate of change of velocity is nothing but the acceleration of the body, that is d square x by dt square. So this Fm will be directly proportional to the acceleration of the body. So this is already derived result. Now from this we can say, that is to remove this proportionality constant, we have to introduce a constant that is nothing but M. which is equal to the mass of the body. So Fm will be equal to m into d square x by dt square. Now, the total force acting on a body can be determined by using Newton's second law. That is, sum of the applied force equal to the sum of the opposing forces. Here, a single applied force as well as single opposing force. So, this F will be equal to Fm, and this will be already equal to m into d square x by dt square. So, we can write the value of Fm as equal to F, which is equal to m into d square x by dt square. Similarly, we can find the force balance equation for the dash part. So, opposing force due to dash part can be considered in two cases. That is, first we are considering the dash part is fixed at one end and the other end of the dash part is free. That is, one end is connected to the fixed reference surface and other end is free. At the free end, we are applying a force F. Due to that, there will be a displacement of the body. So here, due to this force, the piston which moves inside the cylinder, that is represented by X. So now this applied force will be opposed by the opposing force due to a dash part, that is Fb. Because this is an ideal dash part, it is having the negligible mass as well as negligible elasticity. So only there will be a single opposing force, that is Fb. This Fb will be directly proportional to the velocity of the body. That is, Fb is directly proportional to dx by dt. To remove the proportionality, we have to introduce a constant, that is b, which is equal to the frictional coefficient. Fb is equal to b into dx by dt. So now total force acting on a body will be determined by using a Newton's second law. That is, only one applied force as well as only one opposing force due to dash part. So F will be equal to Fb. This F is an applied force and this Fb will be an opposing force. This is already derived, b into dx by dt. So we have to substitute the value here. So this will be the opposing force due to dash part if one end is connected to the fixed surface and other end is free. Then the second case is if both ends are free. That is, the dash part has the displacement at both the ends. That is, at the one end we are applying an applied force. At the other end, there will not be any force, but this will not be a free end, but it is connected to any other elements. Okay, so it will not be kept at free. So in this case, what happens is there will be a two number of displacement because both ends are free. So here, due to the applied force here, there will be a movement of piston inside the cylinder, that is represented by X, and the total dash part will move towards the right, that is represented by X2. Totally two number of displacement. In this case also, this is an ideal dash part, so the mass effect as well as frictional, that is elasticity effect will be zero. Only there will be a frictional effect. So there will be a single opposing force due to friction, which is represented by Fb. This Fb is directly proportional to d by dt of x1 minus x2. So in the previous case, we have written it as dx by dt because we had a single displacement. But in this case, there will be a two number of displacements. So we have to write the difference between the two displacement, x1 as well as x2. Why we are writing this x1 first is we are applying the force at one end, and that end we are getting a displacement as x1. That's why we are writing the x1 displacement first. Suppose if the displacement here is x2 and here it is x1, then we have to write it as x2 minus x1. So to remove the proportionality, we are introducing a constant, that is nothing but b, which is equal to the frictional coefficient. So now using Newton's second law, we can find the applied force is equal to the opposing forces. Here there will be a single opposing force Fb, that will be equal to b into d by dt of x1 minus x2, that is already derived. So this is an opposing force due to dash part. The next one, opposing force due to spring. Now we are considering a spring. So if we are considering a spring, it will be represented like this. Here this also considered in two cases. In the first case, one end is connected to the fixed surface and the other end is free. At the free end, we are applying an input force. This spring is also an ideal spring. So it is having a negligible mass as well as negligible friction. So there will be a single opposing force due to elasticity effect, that is represented by F suffix k. all the opposing forces will be represented by a small letter. That is small f suffix small k. So now here at the free end we are applying an force F. This will be opposed by the opposing force due to K, that is represented by Fk. This Fk will be directly proportional to the displacement of the body. So this is also a derived result. Fk will be proportional to the displacement. To remove the proportionality, we have to introduce a constant, that is K. Fk is equal to this. K will be the frictional coefficient. K into x. So now total force acting on a body can be found out by using Newton's second law. Using Newton's second law, the applied force will be equal to the sum of the opposing forces. Here there will be a single applied force as well as single opposing force. F will be equal to Fk. This Fk is already derived, that is equal to Kx. So now what we have to do is, we have to consider both ends of the spring is free. That is, when the spring has displacement at both the ends. That is, at one end we are applying an applied force, input force F, and other end is free. It is not connected to the fixed surface, but it will be connected to any one of the other elements. Okay, so in this case, at both ends we have a displacement. At the first end, we can say the displacement is x1, that is nothing but shrinking of the spring. At the second end, we have a displacement, that is the whole spring moves towards right, that is x2. So here also we have the two displacements. So we have to write the displacements as the difference in displacement, x1 minus x2, because at the x1 end we are applying a force. So now this Fk will be directly proportional to x1 minus x2, and Fk will be equal to k into x1 minus x2. K is an spring constant. Now what we have to do is, total force which is acting on a body can be found out by using Newton's second law. So Newton's second law says that the applied force is equal to sum of the opposing forces, single applied force here and also a single opposing force. So F equal to Fk. So this is already derived, K into x1 minus x2. So here what we have to do is, for a spring, for the spring, the opposing force will be directly proportional to the displacement. For dash part, the opposing force will be directly proportional to the velocity dx by dt. For mass, the opposing force will be directly proportional to the acceleration d square x by dt square. Next, we will see some of the formulas we are going to use in the problems. So the first one is this, we have studied already, that is transfer function is equal to Laplace transform of output divided by Laplace transform of input with zero initial condition. So by knowing all these formulas, we can easily solve the problems. Okay, so the opposing forces due to mass F, M will be equal to M into d square x by dt square. This we derived already. Then opposing force due to dash part, Fb is equal to B into dx by dt. Opposing force due to spring, Fk will be equal to K into x. Now we have to know about how to find the Laplace transform of the input and output of the mechanical translational system. For mechanical translational system, the input will be the force as well as output will be the displacement. So here Laplace transform of x of t. X is an output of mechanical translational system. L of x of t will be equal to L of x. Instead of t, we can write it as x also. So this will be equal to capital X of s. So inside the Laplace transform, we have the variable x. After finding the Laplace transform, it will be in the frequency domain. Here you have to write the capital letter of this variable, that is capital X. So in the first year, you might have studied the Laplace transform. That is, you know how to find the Laplace transform of f of t. L of f of t will be equal to capital F of s. Similarly, here in L of x of t will be equal to capital X of s. Sometimes you may use the formula like this, that is L of x1 of t minus x2 of t. Instead of t, we can write it as like this, and this can be written as L of x1 minus L of x2, that is nothing but x1 of s. So here we are having a variable as x1, so we have to write it as capital X1 of s minus capital X2 of s. The next, sometimes you may use differentiation of x of t. So d by dt of x of t. So this will be equal to, instead of t, we can write it as like this, dx by dt. Laplace transform of first derivative will be equal to s. Suppose if you are having second derivative, here you have to write it as s square. Then s into, here it is s into the capital letter of this variable x, that is capital X of s. So now, suppose if you're having the difference in displacement like this inside the derivative, then we can write it as L of d by dt of x1 minus x2. Here, d by dt of x1 of t minus x2 of t can be written as, instead of t, we can write it as d by dt of x1 minus x2. So this can also be written like this. See here, L of d by dt of x1 minus x2, L of dx1 by dt minus L of dx2 by dt. So Laplace transform of d by dt will be equal to s into Laplace transform of cap x1, that will be equal to capital X1 of s. Similarly, for this x2 of t also, we can write the Laplace transform as s into capital X2 of s. Okay, now from these two terms we can take s outside, capital X1 of s minus capital X2 of s. So now in this way we can directly write this as s into x1 of s minus x2 of s. So here, otherwise from this expression directly we can write this one. That is Laplace transform of d by dt will be capital S. Then Laplace transform of x1, we get capital X1 of s. For Laplace transform of x2, it will be capital X2 of s. The next, sometimes you may have the equation like this, Laplace transform of d square x of t divided by dt square. In this case, what we have to do is, instead of t, we can write it as simply an x. Laplace transform of double derivative will be equal to capital S square. For single derivative, you will be having capital S. Here you will be having capital S square into x of s. So if you know all these formulas, we can easily solve the problems related to this mechanical translational system. Okay, rest we shall see in the next class. Thank you.